Hey everyone, and welcome. Today, we are going to pull back the curtain on a word that you hear absolutely everywhere, algorithm. But what is it really? I promise you, it's not some kind of dark magic. It's actually just a blueprint. So let's dive in and figure this out.
All right, so here's our game plan. First, we'll nail down what an algorithm actually is. Then we'll look at how we, sketch them out. After that, we'll get into their core components, then see one in action, and finally, we'll figure out what separates a good algorithm from a, well, not so good one.
Okay, let's get right to the heart of it. What in the world is an algorithm? You're probably going to be surprised when you realize that you've been using them your whole life, probably every single day, without even thinking about it. Seriously, have you ever followed a recipe to bake a cake? Step 1, mix the flour and sugar. Step 2, add the eggs. Guess what? You just used an algorithm. It's just a set of instructions to get you from a starting point, your ingredients, to a finished product.
And that brings us to the formal definition. At the end of the day, an algorithm is just a finite, step-by-step procedure to get something done. It doesn't matter if it's for a chef baking a cake or a computer sorting your photos, the idea is exactly the same. It's a clear, repeatable plan to hit a specific goal.
So when you actually go to create an algorithm, it's a really logical process. You start with your input, that's your flour and eggs. Then you define your desired output, the delicious cake you want to eat. The processing part? That's the recipe itself, the actual steps. But there are two really important rules. The instructions have to be crystal clear. We call that definiteness. And the process has to stop at some point. That's finiteness. You can't have a recipe that just says stir forever, right? It has to have an end. So we've established that an algorithm is a plan. But how do developers and programmers actually write this plan down before they dive into writing a bunch of code? Well, they use blueprints, and we're about to look at the two most common kinds. Yep, they use blueprints, just like an architect would for a building. The two main ones you'll see are pseudocode and flowcharts. You can think of these as the rough sketches and the detailed drawings for a computer program. Now, this is a really key distinction here. An algorithm in its purest form can just be written in plain, simple English that describes the logic. Pseudocode is kind of the next level up. It's this hybrid of plain English and some programming-like structure. It's not a real programming language, but it's the perfect bridge between your idea and the actual code. And you might be asking, why even bother with pseudocode? Well, because it lets you focus completely on the logic of your solution without getting all tangled up in the super strict grammar rules, the syntax of a language like Python or Java. This helps you spot flaws in your thinking way early on, and it makes it incredibly easy to then translate that plan into any programming language you want. Okay, the other type of blueprint is the flowchart. And if pseudocode is the written plan, a flowchart is the visual map. It uses different shapes connected by arrows to show you the step-by-step flow of instructions. This makes it super easy to see the path your program is going to take, especially at those decision points where you might see a diamond shape that asks a question and sends you down one of two different paths. Now, here's something that might blow your mind. No matter how crazy complex an algorithm seems, whether it's recommending a movie or landing a rover on Mars, they are all built from just three simple, fundamental concepts. Just three. It's incredible when you think about it. The first, and the most basic, is sequencing. This is literally just a to-do list. You do step 1, then you do step 2, then step 3. It's a straight, predictable line. No jumping around, no skipping ahead, just one thing after another. Next up, we have selection. This is where the algorithm gets a brain. It's a fork in the road. The algorithm asks a question, like, if the light is green, and then, based on the answer, it chooses one path or another. This is how programs make decisions. And finally, the third building block is repetition. You'll also hear this called a loop. And this thing is the workhorse of programming. It lets the computer execute the same block of instructions over and over and over again until some condition is met. It saves us from having to write the same line of code a million times. All right, enough theory. We've talked about the building blocks. Now let's see how that actually snap together to solve a pretty simple problem. So here's our mission, should we choose to accept it. We've got a list of random numbers, and we need to find the biggest one in the bunch. Now, for our brains, that's super easy, right? We just look at it. But a computer, it needs a very specific set of instructions to get the job done. And check this out, this is so cool. You can literally see our three building blocks at play here. Steps 1 and 2, that's just sequencing, one after the other. But steps 3 and 4, that's selection. That little phrase, if the new number is bigger, that's a decision. And then you have step 5, Repetition. It tells us to loop through the rest of the list, doing that same comparison over and over. See? Sequence, selection, and repetition all working together in perfect harmony.
So we've got an algorithm that works. Awesome. But is it a good one? Just like there are 100 ways to bake a cake, there can be tons of different algorithms to solve the same problem. And trust me, some are way, way better than others.
A truly good algorithm has a few key traits. It has to be precise. A computer can't guess what you mean, so there's no room for vague instructions. It has to be finite. It must stop eventually. But beyond that, a great algorithm is also efficient. It has to have a clear input and output. And it has to be effective, meaning the steps are simple enough to actually be done. Think about it like a recipe. Is your recipe fast and uses just a few bowls, or is it slow and destroys your entire kitchen? That's kind of like the difference between an efficient algorithm and an inefficient one.
So why do we go through all this trouble of planning? Because the payoff is huge. A well-thought-out algorithm makes it easy to explain your solution to someone else. It helps you find mistakes in your logic before you've spent hours writing code, which is a massive time saver. And since the logic is separate from the code, you can take that one blueprint and build your solution in any language you want.
But let's be real, it's not always a walk in the park. For really big, complicated problems, I'm talking about things like managing an entire city's traffic flow. Just designing the algorithm can be an incredibly time-consuming and difficult challenge. And sometimes the logic can get so complex that even a flowchart starts to look like a tangled mess of spaghetti.
I think this quote really just nails it. At its heart, an algorithm is all about one thing: breaking down a big, scary, complicated problem into small, manageable, and understandable steps. It's really the art of structured problem solving.
So here's the big takeaway. Algorithms are not just for computers. They are a fundamental way of thinking. Your morning routine, how you plan a vacation, even deciding what to make for dinner. These are all algorithms you run in your head. So I'll leave you with this question. What everyday problem in your life could you solve just by creating a clear step-by-step plan? Think about it. Thanks for digging into this with me today.